Okay, let's get started, please. So just to give you sort of a sketch, the first chapter was, I think, probably a lot of review for people, but reconstructing what you've seen before. And then the second chapter, probably you haven't seen this stuff before. Like it's things, the concept of a limit, and it's seen in this, pretty conceptual, theoretical way. And so the second chapter, I think, is probably the hardest chapter for everybody. So don't worry. Don't worry if it's hard. That's okay. Afterwards, you'll look back on it and you'll see that it's easy. Okay. Don't worry. And then after that, once you get through the second chapter, then the third chapter, when we start really getting into the ideas of calculus, will be easier going. Okay. So the second chapter is sort of to set you up, to give you the right way of thinking, and then after that, when we start introducing the ideas, then it'll be a lot smoother. Okay. So that's just to give you sort of an overview of where we are, or like the structure of this text and the course. Okay. So are there any questions? We have guests today. We have parents in the audience. So ask me hard questions and make me embarrassed. Yes. Yes.
So I think it was the last problem with the homework that we just turned in.
Yeah.
It was the same class. It had like a sine equation, like a complicated sine equation, and it said use the squeeze theorem to like find a limit.
Yeah.
So how are we supposed to find an equation that is like higher and lower than it that could like squeeze it? Like how are we supposed to find those?
There's so a lot of things in math. There's no real method for it. Rather, you just have to look at it and see, come up with your bare hands how to do it.
Okay.
So that's it may have been previously that there's always some way to do it. Right? You just follow some procedure and do it.
Yeah.
But a lot of things from here on in, and in reality, most things are you look at it and here's the method, right? Right, just like this, and then
Okay.
right. So So of course, there's you can sort of there's some problem solving. There's some there are things you can do, but it's there's no real method. Just like there's no real method to creating something, like creating something new.
Okay.
Right? How do you create something new?
Do you think you could just walk us through that?
Sure, absolutely. So what's the problem? I don't remember the problem. I don't remember the
Minus
Absolute value of x minus 1 or something like that.
absolute value of x minus 1. Oh, okay.
Right, and then it's x sine 1 over 1 minus x.
Okay, yeah. Something like this, right?
Yeah.
Use
Okay.
squeeze
Yeah.
theorem.
So it says use the squeeze theorem. Okay. So one trick that can be applied is reminiscing. Okay. Like, does this remind you of anything else? Does this remind you of anything else? Does this remind you of something we saw at the very end of class last time? Yeah. Say again?
So sine of 1 upon x minus 1 upon 1 upon x minus 1 is the same thing as sine p upon p.
It's the same thing as sine.
Sine p upon p, where p is 1 upon x minus 1.
Sine
Sine
p
upon, like over.
over. Okay, sorry, I'm not following you.
Over p.
Over p,
Yeah, where p is 1 over x minus 1.
where p is the same thing as 1 over x minus 1. Okay. Okay. Wait. So is that the same thing? So that's the same thing, right? And then x is going to 1, right? X is going to 1, so p is going to infinity,
Yeah, that's
right?
according to.
Okay. So actually, that's pretty clever. That's pretty clever. I like it. But let me be less clever and say, in class at the end of class last time we did this, right? At the end of class last time we did this, and what did we say about this, right? So we used the squeeze theorem on it, and we said, well, this function actually is trapped between two functions, right? This function is trapped between, this function looks something like this, and it's trapped between, what was it trapped between?
Absolute values and negative values.
Yeah, absolute value of x and negative absolute value of x, right? We said that, well, this is controlled below by this and controlled above by this, right? And we said, the question was, what's the limit as this goes to 0? So the limit as x goes to 0, as x goes to 0 of this thing, and use the squeeze theorem on it. You say, well, look, the one above, right? The one above goes to 0, right? We know that the limit of the absolute value of x as x goes to 0 is 0, right? And we know that this is negative that, so the limit of this guy is also 0, right? And so this thing is trapped between, right? Okay, and so by the squeeze theorem, this thing also goes to 0, right? And so, okay, so here you have something, right? And hopefully, when you see this, maybe you think, oh, this is the same thing as that, right? This is basically the same question, right? What does this look like? It's moved to the right by 1, right? So it's moved to the right by 1. Here's 1, and then you have this thing. Right? Okay. So what are you going to use? What are you going to use to what's bigger than it and what's smaller than it? Right.
I mean, you can do absolute value of x minus 1 and
Yeah.
negative absolute value of x minus 1.
Yeah.
But then if the limit is approaching 1, that's a sudden problem. That means the two limits on the outside are 0, right? But then if you plug 1 into this function in the center, you get undefined, don't you?
That's right. It's not
So how
defined.
is that-
That's not defined.
Okay.
It's not defined there. But that has nothing to do with the limit.
Yeah.
Right? Remember, the limit is not talking about the value at that point, but the value you approach as you get closer to that.
Yeah.
As x gets close to 1. As x gets close to 1, right, this thing goes to 0, this thing goes to 0, and so this thing also goes to 0, even though the function is not undefined.
So it approaches 0, but it's undefined.
The function is undefined there, but the limit is 0,
Okay.
right? Same thing with this one, right? The function is undefined at 0, right? But the limit is 0.
Okay.
Okay. Yeah, Stefan.
How do you know that what you put it between is absolute value of x minus 1 and negative absolute value of x minus 1? Like in a different problem, would I just get what the cosine or sine or tangent is being multiplied by on both sides?
You're looking for a method. Right?
Yeah, I know.
You're looking for
I
a
wouldn't
method.
know how to do it otherwise.
Yeah, exactly. Yeah. But you see that. But we were able to come up with the one for this, right? Somebody, I didn't give you the answer for this. Who came up with it? Who came up with the absolute value of 1 and negative? Was it Mariah? Yeah. Right. So Mariah came up with it. Right. How did you come up with it, Mariah?
I just looked at them like, yeah.
By analogy, right? So that's a method, right? By analogy. So it's not. Yeah, a lot of problems have no method. Although you can, after you play with them for a long time, maybe you start making up methods. Okay, but I think that's actually a pretty important lesson to get across to you that you have to use your understanding of basic ideas. What are the ideas here? One is I had something that I've seen before, right? 2 is translation. Right, translation, and once you hit on the idea of translation, well then, oh look, if that is the translate of this, why not let's translate these functions and use them to control it. Okay, so you have to use your knowledge, right? You've seen translations and you've seen this, and that's basically all you needed to.
Did the answer end up being the limit of x equals 1 equals 0?
Okay. Okay. Other questions? Okay. So, this, if you think of in hindsight, it's not hard, right? Is it hard? Is it hard? It's not.
A harder one would be hard.
A harder one would be hard. That's true. That's true. Yeah. So anyway, so this is sort of what mathematics is like, right? You see this problem, you don't know how to do it, but you start brainstorming. It's just like writing an essay, right? You throw out some ideas. This reminds me of something else. This reminds me of something else, and you think, well, is that going to be helpful? And you look at it directly, and you say, oh, there's a translation involved here. Does that help me? Right? You make a lot of observations. You make a lot of observations, and then see if any observations help you. A lot of your observations might not help you. Okay, but that's how it is. Okay. Just to give a sort of exaggerated example, when you do a PhD in mathematics, then so my experience is doing my PhD in math was like this. And I'd go to my advisor, and he'd say, I've been thinking about a problem, and I haven't been able to make any headway on it. Why don't you think about this problem? And he'd give it to me. Like, oh, okay, right. And I'd go and think about it for maybe a few months. I'd think about it for a few months, and sometimes even more than a few months, several months. And I'd come back. I'd be in the library just thinking and thinking, trying to think of some way to approach it. And then I'd come back and I'd say to my advisor, oh, I'm sorry, Professor. I can't see any connection at all between this idea and that idea that you were suggesting. And he'd say, that's okay. Here's another problem for you to think about that I've been thinking about, but I can't make any headway on this problem. And this was to me this is sort of hilarious, right? Because in a horrible way it was hilarious, because you don't get your PhD until you discover something completely new that's significant to the world of mathematics, right? So your life is on the line, basically, right? Right? If you don't solve some problem and contribute to mathematics, you never get your degree. So your life is on the line, but at the same time, it's sort of hilarious, right? Because here's this guy, and he's a genius, right? He's from a family of geniuses. His brother got his PhD when he was 19. He was a late bloomer. He got his PhD when he was 23 or something like that, 23 or 24. Anyway, they're smart people, and they say like, oh, I don't understand this. Here, why don't you think about it? I can't make any headway on this problem. Why don't you look at it? So just to say that I sympathize with hard problems, the difficulty of doing hard problems. Okay, enough. Okay, so let's go back to the squeeze theorem. So squeeze theorem, and we've already sort of reviewed it. Let me give, let's see. Let me give one simple example that people do often geometrically. Okay. So here's an argument to show that the limit of sine x is equal to 0 as x approaches 0. Okay. So here's one way to approach it geometrically. You say, well, look, if x is positive, and let's look at x here. So x is this angle, okay, and this is the unit circle. Okay. Where is sine x on this picture? The y coordinate, right? So it's this length here, right? This length here is sine x, right? And there's x right here, but x is also in another place. What's the length of this thing here? What's the length of this thing?
90 degrees. Or the radians.
Yeah, so it's the so what's the length of this thing? Does anyone know?
Is it x?
It's x, yes, thank you. I thought I had given it away, but clearly I didn't. Right, the length of that is x, right? And so what you see is that sine x, right? The shortest length is the perpendicular, right? So you see that sine x is smaller than x, right? If you drop straight down, that's a shorter length than going on this curved line to the ground. Right? So the curved line of length x is longer than the straight line, which is of length sine x. Right? Okay, and we also see that this thing is bounded below by 0. Right? It's at least as x for x positive, as we're going down to 0, this thing is bounded below by 0. Okay, everyone all right? Yes, Stefan.
You said x is the curve?
X is the angle here.
Mm-hmm.
And from your knowledge of radian measure, if this is a unit circle, then the arc length of this subtended arc is x. Okay. So,
why is the angle x again?
because I said it was x.
Oh.
Yeah, we just called it x.
Okay.
Suppose you have an angle x, then this thing is sine x, and this length is x. Okay. So then, and then you just use the squeeze theorem, right? So take the limit as x goes to 0 of this thing. What happens to 0 as x goes to 0? Well, 0 is just a number 0. Right? So 0 doesn't change, right? 0 just stays at 0, right? As x goes to 0, this goes to 0. And so what happens to sine x? Well, the limit of sine x is going to be 0. So by the pinching theorem, or by squeeze theorem, since the limit of the lower function is 0 and the limit of the upper function is 0, we know that the limit of sine x is 0. Right? Because the guy above and the guy below both go to 0. Both go to 0. At least from the top, from the right-hand side, right? As 0 is positive, right? But you can do the same sort of thing for the left-hand side and then show that the sign is 0. Okay. So that's one example. Another example that I'm going to leave out is that the limit of the cosine as x goes to 0 is 1. So I'm just going to leave it out. In favor of this one, the limit of the limit of sine x over x. Okay. What do people think? Yes.
Well, why can't you just so what's the point of using the squeeze theorem like that situation? Just because if you plug in 0 into sine x, you also get the limit of 0.
How do you know that you can plug in the sine x? Plug in the 0 to sine x?
Well, you're just assuming that it's the case.
Well, even if the function is defined there, right, doesn't mean that the limit of the function is the value of the function there.
Yeah.
Right. So you don't know that if you plug in the value of the sine, that it's actually going to equal to the limit. This is what shows you that it's okay to plug in.
Okay.
Yeah. So you basically at this point we don't know if it's okay to plug in. Here we're finding out that it is okay. Okay. Yeah. Okay.
Why are you just taking the limit from the right side of 0?
Just for the sake of the picture.
Oh, okay.
Yeah. Because I was using a positive angle here.
Okay.
But you can do the same thing with a negative angle. And
Okay.
do the same thing.
Are those two separate examples?
So I'm skipping this example.
Oh, okay.
I'm skipping this example.
Sounds good.
Okay. So what do people think about this one? Limit of sine x over x.
Would you use that theorem B when you separate the
Oh, you're thinking
I don't know if you do the quotient thing.
the quotient thing. The quotient thing. Maybe you could, right? What happens to sine x as x goes to 0? You get 0. What happens to x as x goes to 0? You get 0, right? Right. So you can't use that theorem because you need the denominator to be non-zero.
Okay.
Right. But that would be a good idea if it weren't so. Any other ideas? What do people think about this? Does anyone know the answer to this? What's the limit of sine x over x? Yes. It's 1. Yeah, it turns out to be 1. Turns out to be 1. And it's not because 0 over 0 is 1. Okay, don't tell me that. Okay, it's not because 0 over 0 is 1. But you can see this using the squeeze there. Okay, so again, we're going to do something geometric. Let's do it like this. Okay. So here again, let's use the unit circle, and let's draw an angle x here. Sine x we saw before, right? Sine x is here. Sine x is that height, right? This length here, well, x is here, right? X we also saw before. Right? And what's this height here? What's this height? Well, let me ask you this first. What's this length up until this point here? What's this length? Cosine? Okay. So what's this length? What's the height here? So you have two triangles. This is cosine, this length is cosine, right? This height is sine. This length is 1. So what's the height?
What's proportional?
It's proportional. It's these are similar triangles, so you know that it'll be sine x over cosine x. Right, because sine x to cosine x will have to be this angle to this length to this length. Right? The ratio of this length to this length has to be the ratio of this length to 1. Okay. Everyone all right? Okay. Any questions? Okay. So now we're going to look at areas actually. So what's the area of this triangle? Well, it'll be 1/2 base times height, right? So 1/2 base times height, and that's smaller than the area of this circular sector. The area of the sector. Does anyone remember the area of the sector? No, that's okay. X over 2. You can work it out. I'm sure you could figure it out if I gave you a minute. And then what's the area of the last one? It'll be 1/2 base times height again, right? So 1/2, 1 times sine x over cosine x. Okay. So consider areas. Yeah, go ahead.
Sorry, how did you get x over 2?
That's the area of this sector here, the circular sector, where the angle is x.
Oh.
If the angle is x, then the sector is going to be x over 2.
Is there an easier way to get to the answer?
This is the easiest way that I know.
Go on.
This is the easiest way that I know. There's a much harder way to get to the answer.
I don't want that one.
Okay. Yeah.
Wait, sorry, what's the answer?
No, we're not done yet. We're not.
Okay.
Done. No, Gwyneth is just saying, can we stop now? Sorry. Okay. So I'm going to do something very simple, which is to divide by everything by 1/2 sine x. Okay, so I'm going to cancel out. I'm going to divide everything by 2. Right. I'm going to get rid of the 1/2s. I'm going to multiply everything by 2. Excuse me. And I'm going to divide everything by sine. So I get cosine x. Again, I'm taking x positive, okay, because of the picture, but you can do it the other way as well. So you get x over sine x, and you get 1 over cosine. Okay. Okay, and now we use the squeeze theorem, right? So now you use the squeeze theorem. Let x go to 0. Let x goes to 0. From the example that we left out, but let's just assume it. From the example we left out, what happens to cosine x? Goes to 1. This goes to 1. 1 over cosine x is going to go to 1 over 1. Right. It's going to go to 1 over 1. And so the thing in the middle is going to go to 1. Yeah.
The function in the middle, though, is reciprocated from what we had at the beginning.
Yeah, that's true. That's true. That's true. But this is going to be 1 over that, right? So this will go to 1 also. Or I could turn this upside down if you'd like. I could say 1 over cosine x is bigger than sine x over x is bigger than cosine x. Right? If you'd like, I could turn it over now and then use the squeeze theorem. Or you can use the squeeze theorem and then turn it over. Okay, so that's what we get.
Are you saying that sine of x over x is equal to x over sine of x? Like because of all the stuff we did between?
Say one more time, Stefan.
It's like you ended up taking the limit of the reciprocal. Would that mean that it's the same thing as the function?
So what we showed here, suppose we don't turn it upside down first. Okay. What we end up showing is this, right? X over sine x. As x goes to 0 is 1. Right? Okay. Then if I ask you what's this? You'd say it's going to be 1, right? Because this thing goes to 1, right? But what's this? This is what I'm looking for.
Cool.
Any questions? Any questions? Okay, so that's actually a pretty famous fact that the limit of sine x over x goes to 1 as x goes to 0. Okay. Yeah, if you take a physics class, at some point they'll undoubtedly use this sort of thing. They'll say for small theta, sine theta is basically theta, and then you'll make some sort of approximation that sine theta is basically theta. And why can you do that? Well, because the limit of the ratio tends to 1, right? For tiny x, sine x over x is basically 1. So sine x is basically x. Okay. Okay. Okay, a couple more things. I'm just gonna give it to you. So some miscellaneous theorems from this section. One is that if you take the nth root of something as x approaches a value, then it's okay to just substitute in the point. Taking the limit of an nth root function as x approaches c is just going to be the nth root of c. Okay. Another one, limit of sine x as x approaches c is just going to be sine c. So along the same lines, sine x, we saw earlier that you could put in 0 here. In fact, it's true that you can do this for any point, and it's also for the cosine. Okay, so these are we asked earlier, what kind of functions is it okay to just plug in the value to figure out the limit? Well, here are a few functions for which that's possible. Okay, here are a few functions for which that's possible. Okay, and just make one observation. Notice that what we're doing, you could think of like this. It's saying that it's saying this sort of thing. The limit of sine x as x approaches c is same as the sine of the limit of x as x approaches c. Right? Because what's the limit of x as x approaches c? C, right? So if I write it, I could write it like this, or I could write it like this. Right? I'm saying the same thing. But this second way of writing it makes it clear that some sort of switching is going on. Okay. Some sort of switching is going on. That you can pass the limit through the function. Okay. You don't have to know that. I'm just gonna put that in there. Okay. Okay. So this leads us to a definition or an idea. Okay. This idea is called continuity. Continuity. Okay. So if the limit of f of x as x approaches c actually equals f of c, then we say f is continuous. Continuous at c. And I'll quite often abbreviate that as CTS. It's continuous at c. Okay. Okay. So to use that, the abbreviation was CTS. Continuous.
Thank you.
So, okay, so all we're saying, so to use that new language, to use that language here, what we're saying is that the nth root function is continuous. The sine function is continuous. The cosine function is continuous. In fact, at every point. Okay, so that's how you want to phrase it. So rephrasing our previous section, some results. From our previous section, you could say, 1, polynomials are continuous at every point. Right? Polynomials are continuous at every point. Right? We saw that the limit of a polynomial as x approaches c, you just evaluate the polynomial at c. Right. And another thing we saw was that rational functions are continuous at every point where they're defined. So every point in their domains. Right. We couldn't have the denominator being 0. But outside of those places where the denominator is 0, the rational functions are continuous.
What do you mean by rational function?
A polynomial over polynomial, a ratio of polynomials. So p over q, so the limit of p over q is actually going to be, just evaluate as x approaches c, is going to be p over c over q over c, as long as q of c is not 0. There's sort of the analog of rational numbers, right? Rational numbers, you've got an integer over an integer, you have a ratio of integers, and the rational functions, you have a ratio of polynomials. Okay. Right. We also have that the nth root function is continuous, and we also have that sine cosine are continuous. Okay, so just to use the new language, yes, Stefan?
No, I didn't know if that was an n, but I understand that.
N3, yeah, the N3 function is continuous. Yes. So,
So you're just saying that like there's no cap in outputs then, so like it's okay to plug in.
that's right. That's right. So these are functions for which, if you want the limit, you just plug it in.
Alright.
Is that continuous last word?
Yes.
Sine, cosine?
Yes. Sorry. Yes.
All right.
Do you have another question, Stefan?
What's up?
Oh, I see. Do you have another question? Keep on asking. I don't mean to mock you. Okay. Okay. Ask questions. It's actually really helpful if people who enjoy asking questions ask questions, because the people who are shy don't have to ask questions. At least that's what some students have said in the past.
I have a question.
Oh yeah. Yes.
So like for number 2, if,
Yes.
so if Q, what would happen if Q at C did equal 0? Like,
If it equals 0, well then
or would it just not be like?
it sort of depends. It sort of depends. What this theorem tells you is that as long as the denominator is not 0, then you can do the plugging in.
Okay.
But it doesn't say about otherwise. In the other case, well, maybe sometimes it'll work and maybe sometimes it won't work. Okay. Let me do an example of something that's a little bit more strange. So here you have a function, and the function is this actually is a good example for you, Sarah. Here you have this function. If x is not equal to 5, and the function is equal to 4 if f equals 5. So you have this rational function. You have this rational function. It's not, the denominator is 0 there, 0 at 5. But we put in a value there. Okay. So the question is f continuous at every point? Okay. So I'll let you think about it, actually. Is f continuous at every x, at every point in the real line? Okay. I'll let you think about it for 1 minute. And feel free to talk with each other. Okay, so what are people saying? Other than Stefan? Victor?
I say it's not continuous because the limit of the first function is not 4. I don't think.
Okay. So are you saying that it's discontinuous everywhere or discontinuous?
No, just at x equals 1.
So Victor says not continuous at 4 because the limit of this thing as x approaches 4 at 5, excuse me, 5, it's not 4. Yeah, Kelly.
I'd say it is continuous because I think the limit is equal.
Okay, it is continuous for the opposite reason. You're saying that you took the limit as x approached 5 of this thing as x goes to as x goes to 5, and you got 4.
Yeah.
Okay, so one of you has made some calculation error, but we'll check it. What about everybody's focusing on the point x equals 5? What about x not equal 5? What? Yes, about.
What I did was I plugged in both 4 and 6 into the top equation, and I saw the answer to when I figured it out, it was 3. It was 3 on when I plugged in 4, and it was 5 when I plugged in 6. So I kind of assumed that it might be 4 if I plugged in a number between those two, and that the bottom one just kind of fills that gap, so it is continuous.
Okay. Let me ask, if x is not equal, let's do the x not equal to 5 first. So if x is not equal to 5, is the function continuous?
Yes.
Yes, absolutely, right? Because the function is rational, right? And what we just said was that functions that are rational are continuous wherever the denominator is not 0. Okay, so f is continuous for all x not equal to 5. Now the only question is, what about at 5? Okay, and so that we're asking is the limit of f of x, right? Is the limit as x goes to 5 equal to the values function at 5, right? Is the limit of the function as x approaches 5 equal to the value of the function at 5, which is 4, right? So that's our question. Yes, Dia.
Yes.
Yes, it is. Yeah, it turns out to be. Victor, you must have made some calculations.
Yeah, I did.
Oh, you did? Okay, good. Yeah. So, right, you get x minus 5, right? And then, what? X minus 1. Okay. You get x minus 5. That's x goes to 5. Right. And then you say, well, this is just going to be 4. You check. Right, the left-hand side, the limit of the left-hand side is 4, the right-hand side is 4, and so you get that equal. Okay. So the function is continuous, so f is continuous at 4 also, at 5 also, right? And so it's continuous everywhere on the line. Okay. Now notice if we had chosen a different value here, if we had defined it to be 3 here, then the function wouldn't be continuous. There, right? We would have messed up, right? But if we choose it to be the right value, then we can make it continuous there. Okay, so we can fill in the discontinuity. So sometimes the moral of this example is that sometimes it's possible to fill in or to remove a discontinuity. This is what the book calls creating a continuous extension. Okay, so, right. This function f of x that we're dealing with here, it basically looks like x minus 1, right? It looks like x minus 1, except it has a hole at 5, right? It has a hole at 5, right? This is the graph of that function, right? Without the extra definition. Okay. But you see that if we define, just define it, if we define f of 5 to be 4, then we fill in the hole, right? And so that's all that just happened. Okay. And so you have this function that's discontinuous, but it's possible in this case to create a continuous extension. That's not always possible, right? If you had some function that went like this, you have some function that went like this, well, no matter how you fill in the hole, it's still going to be discontinuous. Okay, so not always possible. Yeah, Mariah.
To create a continuous extension, do you have to make a piecewise function?
Yeah, basically. So you have the function as originally defined, and then you add on, you define it by hand at the points where it's not continuous. Yeah. Other questions? Anything? So, let me give you a couple more useful things. So one, if f and g are continuous at some point, then one, their sum is continuous there. Two, their product is. Three, their any number times one of them is, right, where alpha is some number, some constant number, and four, as you might expect, the ratio is as long as the denominator at C is non-zero.
Would number 3 be true as well for G?
Yeah.
What is the third one?
The third one says if you multiply it by some number, it's still going to be continuous. So if I had sine x, we know sine x is continuous. 5 sine x is still going to be continuous. You multiply it by some number. So for example, if I look at sine x over x, this is a continuous function over a continuous function, right? And so this is going to be continuous everywhere. It's continuous except where x is 0. Everywhere except at x equals 0. Right? By property 4. Right, you know that the ratio of continuous functions is still going to be continuous. Okay. And in this case, you can remove the discontinuity at 0 because we know the limit, right? The limit is 1 there. So we actually can fill it in with a value of 1 and make it continuous. Okay. So removable discontinuity except a removable discontinuity at 0. Okay, so this is good, right? You can take products of functions, right? You can have sine x cosine x times x squared plus 1, and you know that this function is, all you have to do to find the limits of this function is to evaluate it. Right? It's continuous, right? So you see that this function, this set of facts is really useful to you. Okay. There's one last fact, which I'm going to try and squeeze in, which is that if f is continuous and g is continuous, then g of f is continuous. So if you compose functions and the functions are continuous, then the composition is still going to be continuous.
The other way around.
It will work the other way around as well. Yeah, I'll get back to this one at the beginning of next class. But just to give you a quick example, if I ask the limit of the square root function of the square root of sine of x, well, this is just the square root of the sine, and you know that the square root is continuous and the sine is continuous. So all you need to do is evaluate. Okay, this is great, right? Otherwise, it's pretty hard to figure out the limit. Okay, that's it for today.
Since You got it into 2.3, should we just do?
Yeah, so again, I'll have to send out an adjusted assignment
Okay.
for yeah. Don't look at your assignment. Don't look at the syllabus for the assignments. I'll try to send out an adjusted one.
Okay.